Yo, yo, yo. What's up? What's up? Welcome back. Today we're working on my x86 operating system called Stream OS for now. It's written in Rust, and we're starting to get to like a semi-working operating system. It has no user space, but it does have kernel space. So we have an operating system. It boots in a virtual machine. It has like some form of concurrency, some form of like I/O with the user. So we have like graphics for drawing stuff, as well as like a text output to the serial console, which can be piped through in the case of a virtual machine to like the terminal for standard in out of like our program. We have unit testing that like correctly flags failures when we boot the OS to the host OS when we're using a virtual machine, so we get like nice linting and stuff like that. We have like an Ethernet stack that goes for like from PCI Ethernet to like address resolution to TCP and UDP, and we've proven that we can do like a web server, stuff like that. And we've got like kind of like keyboard input to the point where we can like run a game. And we can do that like while doing other stuff. So here's like a simple little brick breaker game, no scoring or anything, but it does like I can move the paddle around, I can like draw the bricks, etc. And while that's running, I can like talk to my server, and if I like send a string to it, it'll like send it back over TCP. Great. This is done with like Rust's concurrency model, which is like async. Well, I shouldn't say Rust has a concurrency model. There are multiple. But this is making use of Rust's async runtime. I guess I shouldn't say runtime either. Rust async infrastructure, we'll call it. And their async infrastructure kind of looks like this. So you like write an async function. Let's see, like, find a good example. Maybe I'm trying to find like a short and sweet one. Here we go. So you write like an async function, right? You put async in front of it, and oh, that's a bad example. God damn it. Hold on. What is a good example? Maybe here. One sec. Pull, sender, receiver. This is another bad example. Here we go. No, bad example. Okay, anyways, the way it works is you write like an async function, and when you like do stuff, you might want to like wait for something to happen. So, for example, we might want to like read a packet from the Ethernet driver, and when there's no Ethernet packet to come in, we just like say, hey, that's not going to happen immediately, so we're going to wait for that thing to happen. So here we call like RTL139, which is our Ethernet driver. We read on it, and at the end of that we say, oh wait, great. So you can write like normal functions where you just have like checkpoints, basically, where you say like, here I'm gonna like get a TCP frame, and then once I handle it, I'm gonna wait for the handling to work correctly, and then I'm gonna write to the Ethernet driver. I'm gonna wait for that to happen correctly. Great. And what they do under the hood is these get converted into like these like future types. Where the implementation of future is probably, we look at this. The implementation of a future is basically like a thing that you like poll you for readiness. So like every once in a while you like look at this feature and you say like, are you ready? Are you ready? Are you ready? And he'll be like, nope, not ready right now. I'm busy. Like I haven't got my data yet. So go fuck off, do something else, right? And what happens is you like have this feature, and all the async thing does is like an async function just creates one of these features. And so it's like up to users of these features to like put them somewhere where they will be run until like polled at a reasonable rate. So like a very, very naive implementation would just to be like, call this poll function like over and over and over again as fast as you fucking can until you get like, until it says it's ready to go. But like a more intelligent thing to do is you like poll it and it says like, I'm busy, right? and you just don't pull it again until you think it will be ready. And so like the infrastructure has this like context that has like a waker inside of it, and the idea is that like you will here. Let's see. You might want to like have like a thing over here, like a reader, Rx. I don't know why we use Rx into TX, but the X, this means like I'm reading something, right? And this guy has a poll, and so I'm gonna be like, hey, you ready yet, dude? He's gonna be like, nope, not ready. And we could, then what happens is like somewhere over here, at some point, somebody's gonna write to the transmitter side, right? And they're gonna go here, and they're gonna say like, I've got some data for you, here you go. And he's gonna like, send the data over to the reader side. And you could actually flag at this point that the reader is ready to read, right? And really, we shouldn't have to pull again until this happens. And so that's what like the Rust waker is for. So basically what should happen is I should, when I construct these guys, there's like a channel between them. When I poll this guy, I give him a context that says like, here's where I'm polling you from. And he should like ship that all the way over here, right? So that when he has this like little like waker, we'll call him ZZZZZ because he's sleeping. What happens is when he sends the data over there, he kind of like pokes this guy and says, wake up now. And then we pull him again. And so the idea is that we should only ever really pull this guy like a couple times. Once to check his initial state and like give him his wake up context, and only ever pull him again when we're told to wake up. And we like kind of do this right now. The way we do it right now is for my operating system, we kind of have this like extra piece of knowledge, and that is that if we are I should say in the current state, we have this extra piece of knowledge, and that extra piece of knowledge is that if we are executing a feature, our CPU literally has nothing else that it has to do. So he just like, if we are not ready to run if the feature that we're polling is not ready, we just turn off the CPU. We say halt. And this just says like, don't fucking do anything. Don't try to advance the instruction pointer. Don't do shit. Just like go to sleep. And what happens is the only time, like, you would think that this would like stop you from doing any work whatsoever for like the rest of time, but there's this extra thing that happens where when a interrupt fires, i.e. like, let's say that we have like an Ethernet card over here, Ethernet, physically, this is like an Ethernet card, and it's like physically plugged into the CPU. Kind of. Right, we're kind of glossing over details. And what happens is, like, he's got, like, a wire coming out of it that goes to, like, the outside internet. And when a packet hits here, he goes, like, CPU, wake the fuck up, please. It's time to do some work. And that will trigger an interrupt that'll, like, kick the CPU out of its current context. And that's all, like, hooked up in hardware. I don't have to do anything to get that. Well, you do have to do some stuff. But, like, that kind of comes based off of, like, where things are plugged in on the CPU. So that kicks us out of our sleep, and we then go and we check if we actually should pull our futures, and if we should, then we do some work. Great. All of that's fine. But there are some problems with this approach. One is that we have like one static variable that is like accessed from the interrupt context. The idea is that like there are interrupts that will fire that we shouldn't pull our features on. For example, our clock is hooked up to an interrupt line, and so like every like 4 milliseconds, it will wake us up, right? Unconditionally. It's just going to be like, oh, time to wake up, like, because like I count, my number went up. You got to know when my number goes up, right? I want you to know when my number goes up, and we kind of do want to know that, right? But in reality, that doesn't mean that we should like do work related to like Ethernet because the number went up, right? That's unrelated. And so we have this Boolean that we store in static space that just says like, does anybody actually want us to like check? Does anybody want us to like poke our features and see if they're ready to go? And every interrupt will like, depending on what happens, might set this. And that works, except there's like an assumption here that there's only one executor running, right? Because this is a static variable. It's like the only, like everybody's talking to the same executor. And that's going to become a problem if we want to do multi-core. So what I'm kind of thinking for this stream, or kind of like where I'm thinking of going, I guess, is right now we have one CPU, and he's executing he's running like one future executor that runs like one task called a future. And this is just like an async function, like we said before, right? Just like a normal function that you wrote the word async in front of and has like breakpoints that it can jump to do something else. And how we kind of package this up is there's these like combinators, I think there is what you would call them, like ways of like packaging up multiple futures together into one, right? So if I have like async function 1 and async function 2, I'm going to draw these a little bit lower. We'll call them F1 for function or future. I don't really know which one I want to say it is. And F2, right? You can actually like package these together into like one mega future. And this guy will like basically hold each of these inside, and he'll say, I'm only done when both of these guys are done. And I'll like check them both over time. But like really, I'm not going to say I'm finished until I'm done. And so what we have right now is we have like this mechanism where we have like their CPU is running one future, and when he says to do something, he checks basically all of them, right? Which can like start scaling pretty shittily, because what you really want is you want these to be like independent, so that if you have like multiple CPUs, which is where we're going, with this scheme, there's like, he doesn't really know that these guys exist. And so even though all three of these guys can be like happening in parallel, this guy can't do anything. Right? And so what we kind of want to do is we kind of want to have like, if they're completely unrelated, we kind of want like this, where we have them kind of just like queued up. And then the idea is that like each CPU could like take some if they want to pick them up, right? So we'll have like a queue of work, and each CPU will just grab whatever work is available. So that's one thing we want to do, is we want to split up work into smaller chunks. We want to support running futures from multiple CPUs. So we want to support moving work to other threads of execution. And I guess we also want to support, while we're here, we can kind of get more efficient than the original workflow. So the original workflow, we have like this, right? And say we have like 100 of these guys, right? Say what happens is we have like our TCP sockets, maybe. We have like a web server, right? And he's servicing like 100 connections. And we could either, so if with the current mechanism, when something happens that's interesting to any of those 100, we're going to check them all. And that's like such a waste of time, because we know which one we want to check. And so what we also want to do here is we want to have like, we want to have a way of signaling which one is ready. And that also helps with multi-core, because it tells us which CPU to wake up, etc. So yeah, that's the other thing we want to do, is we want to signal which future is ready. And so those are kind of like the goals of what we're going to be doing here. And so really what we're going to do is we're going to try to take this like signal of time to poll right now, and we're going to try to move that into a like, tie that to a specific future. And maybe we're going to try to like pass in a bunch of futures at once for now, and keep like a queue of them. And I think maybe also what we want to do is maybe from within a future, we might want the ability to spawn more in this like global queue, right? So like, say I have like a TCP listener, right? I'm coming in and I'm saying like, when someone connects to me, I want to like stick this other chunk of work on there to service their specific connection. Yeah, so that's those are like the kind of like the goals of what I'm doing here today. And I think I'm just going to start like poking around and seeing what makes sense. I think I'll just go from there. It's like 1425-ish. So the first thing we want to do is what? We probably want to like associate, remove the global context. Remove the global poll context. Right, so like basically our interrupts, when they fire, they should be tied to a specific feature. And so right now we have this like static boolean, and our all interrupts just call this like wake up executor function that just like sets that to true, essentially. Um, yeah, so I guess I'll start trying to look at what would it look like to get rid of that. We have this waker already. Right now it just uses the static thing, but it doesn't have to later. I think what I'm going to try to do is just start piping that into where it needs to go. So basically all uses of this wake up executor function should eventually go away. And maybe we'll just take maybe try to start somewhere simple. So maybe we'll start in the Ethernet driver. And in the Ethernet driver, we have this very simple function, right? He says, when I get an interrupt that I received a packet, wake up the executor. Sure. But the question is, what do we really want to do when this happens? What we want to do is we want to poll our future that's related to Ethernet reads, right? So really we have this RTL 8139. Here we have a future that says when there is data in the buffer of the Ethernet driver or of the Ethernet card, I'm ready. And so really we want to associate this wake up with this future. Which means that probably on the first poll of the future, we need to propagate that information over to the interrupt handler. So I guess the first thing that we're actually going to work on is this is kind of like a subtask of this. And what are we going to do? We are going to propagate waker from Ethernet future to Ethernet interrupt context. Cool. So let's think about this. In this case, our Ethernet driver, we should only ever really have one person waiting for an Ethernet packet at a time. I guess you could argue that multiple threads could wait on it, and whoever gets there first will read it. But in reality, there should only be one pipeline of Ethernet packets. They can dispatch to multiple threads depending on what the packet does. But the first, there's only one reader of this packet. There's a serial list of things that you would have to do, right? You get the packet, and then you do some stuff with it, and you get rid of the packet. Done. And so because of that, we should probably make this a mutable reference to the driver required to read, right? We want to be the only person interacting with this. But that doesn't really work because we have a writer as well. You could have many, many people writing to the Ethernet driver. You only just have one person reading from it. Let's see. We also have this write function, and he awaits something. Transmit data and wait. Right, so he waits for transmission to finish, and that also triggers an interrupt. So we actually have multiple interrupts that we have to worry about, right? One is on the transmission side, and one is on the reader side. Okay, so let's think about this. Eventually, if we have multiple CPUs running and they're all trying to wait for something to happen, we could have up to we could have these how do I say this? We have multiple people that we're going to wait on, right? There's also the concept of if you have lots of writes at once, you might have lots of people waiting for these at the same time. So where I'm going in my head is that there's an unbounded list of potential futures that could be waiting at a given time. And they could be coming from an unbounded number of executors, right? You could have 4 different CPUs all waiting on different futures. And so they will be woken up independently, probably. And so really what we have to do is we have to propagate any potential number of wakers to the interrupt handler, probably. Let's look at the Waker API. where I'm going in my head is that uh the future executor right now, he uses one static, right? But maybe what he'll want to do is he'll want to say, I have futures 1, 2, 3, and 4. Let's draw it out maybe. Maybe he'll say I have like 1, 2, 3, 4, right? And if these are kind of like split up in memory directly like this, each one of these could like be associated with his own waker, maybe, right? And so this, like, I could also have like W1 that points to this guy, W2 that points to this guy, etc. And so, like, in that case, I would actually kind of want my like interrupt handler to like maybe walk a list of wakers, right? And like wake up only the futures that are matter. So say that like 1, 2, and 4 are related to Ethernet, then maybe I would like wake up these guys and only these guys. That seems like it might make sense, but then we kind of have this like complexity within the Ethernet driver itself. In the interrupt handler, we would have to wake all of these guys, and that might become like kind of expensive, is what I'm thinking, right? Like you don't want to like in your interrupt handler, if there were like 1,000 of these guys, we wouldn't want to walk 1,000 elements in an array and do an atomic operation on all of them. That seems like crazy to do in an interrupt handler, because your interrupt handler is supposed to be short and sweet, right? Because they fire very quickly. And so maybe what makes sense is for each driver, maybe we flag, we like propagate some status variable, and somewhere else is where we actually propagate the wake ups. So that could make sense. So we would actually maybe have like a service future 5, right? And our interrupt handler only wakes up this guy, and then he wakes up all of the other ones from within his context. That seems kind of reasonable. Then all of the complexity of managing who needs to be woken up, etc., can be offloaded to like non-interrupt code, which is much nicer to work with. Okay, that seems reasonable. And I'm looking at this Ethernet driver, and I'm actually thinking that this isn't the first one I want to tackle, actually, because it seems kind of too complex. I want to start with something even simpler, which is the sleep implementation. Waker from sleep future to timer interrupt context. So let me just make sure I haven't actually changed anything. And let's actually go to the sleep implementation. I like that one better. So what we have right now is let's see. On tick, maybe? Yeah, here we go. So on every interrupt from the clock, we increment our like concept of time, and we call this like wake up if necessary, which just says like if I have somebody that's waiting on a specific time, I will wake up the executor, and that will automatically check all of our wake ups, or all of our sleeps, but maybe we only want to prop check the sleeps that are related. And so if we think about what we were just saying here, where we might have like, maybe we'll draw it out again for reference. So we'll have like, in our interrupt handler context, in our interrupt, we will have a single waker. We'll put him in a box. Waker. We'll call him W. He is going to talk to a single future. So this is going to be, I guess, like futures. He is going to talk to a future service. And he is going to have like a list of like all of the people who are waiting on him. So he's going to have like W2, W3, W4, right? If they're like 4 or 3 people sleeping. And these are going to connect to future 2, 3, and 4. Like this. These are connected like this. And so what we have to do is we have to keep a list of all of the futures that are sleeping here, which we already kind of have here. We already have a list of everybody who wants to be woken up because we have to store their times anyways, right? If somebody was like, I want to sleep till 3 seconds from now, we have to like write down when 3 seconds is and remember that for later. So we already kind of have some state here. And all we have to do now is associate like the waker with that specific state. Great. We have to replace this wake up executor with a single, probably static variable. Maybe not static. Let me think about this. No, not a static. We need to propagate a waker, a single waker into this interrupt context. And so probably what that means is we don't get the waker until somebody polls. So what happens is this service function, we already have this guy. He already exists. He's called wake up service. And what happens, what we have to do is we have to say, we are the only person servicing this. That's great. And when we are polled, we will probably just have to tell the interrupt handler where to wake us up. So let's think about this. Which means we might need to convert this guy into like, instead of an async function, we might have to convert him into like a manually written future. So we could say impl future for wake up service. Let's see what that looks like. Maybe we'll call him, maybe we'll make an internal thing. I don't know, we'll think about it. So what would this look like? We'd have to implement poll for him, which is this guy. And his output is probably nothing. He's never going to finish. He's going to loop forever. And the important piece here is that we need to get the waker. So we're going to say waker is the context that we're pulled from. Get the waker. And now we need to put that somewhere. So presumably, since our interrupt context, somewhere we construct this guy. Here. So we construct here the wake up service as well as the wake up list. And so here we could like create a channel for these guys to talk between each other, right? We could create a like let tx rx is equal to, let's say for now we have a lock free queue somewhere. Yeah. That sounds reasonable. So we have a lock free queue. And here we'll make a queue of size 1. No. Shit. Okay, what I was thinking was we could make a queue that has a size of 1, and we could say that we'll push in an element, and we will take the last thing that was set from our service loop. When we pull the service loop, we find out which waker is associated with it. Great. But if we say we pulled it like multiple times, then all of a sudden that wouldn't work anymore. But I think that's okay for now. Eventually, we'll probably have to have a better type for this. But for now, we'll just say tx rx is equal to lock free queue channel size 1. So the idea is that on the very first poll of our wake up service, we will put the waker in this guy. So we need to say waker tx is a lock free queue sender that sends wakers. And in our interrupt wake up list, we need to have a waker rx is a lock free queue receiver wakers. That seems pretty reasonable. Type waker is not found, so we need to import that. I think that comes from here. Here we'll say waker is a option waker, and on update we'll say if waker rx self waker rx if we read a value from him, which I think should just be a pop. So if we pop something from him, is this an async function? No. We just have a non-async pop. Okay, so if we pop something from this guy, we assign that to our waker that we're keeping track of. Some waker like this. Great. So now we have like a specific waker to wake up. And then instead of wake up executor here, we call self.waker.wake, I think. Oh, we also have to check this. So if we have a waker, it's equal to self.waker. I think you have to do like as ref here. To make sure that we don't like try to take the value out. We can just say waker.wake by ref, I guess, because we don't want to consume it. Great, that makes sense. And then here we try to send the waker over. So we say waker tx send or push, I think. Great. We push the waker we got. We have to clone the waker, I think. Nice. Which is legal and valid and what you're supposed to do. And this guy returns results. And so we'll just say, we can kind of ignore it, right? If their queue is full, we fail to push something because the queue is full. That just means we've already pushed it. And I'm going to assume for now that once you pull it one time, that waker context is valid forever. That's what I'm going to assume for now. I don't know if that's actually true. Let's see what like Rust's documentation say about this. So they say, registering the current test for wake up, but the value is not yet available. When a feature is not ready, it returns poll pending and stores a clone of waker copied from the current context. Waker is woken once the feature can make progress. Blah blah blah. When a signal arrives elsewhere, blah, 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 wake is cloned, or is called, and the socket's feature task is woken. Great. Once a task has been woken up, it should attempt to poll the feature again, which may or may not produce a final value. Note that on multiple calls to poll, the waker from the context past the most recent call should be scheduled to receive a wake up. Okay, so this is indicating that we do actually have to update. So, I guess we'll just, which is why this, like, idea of a lock-free queue as our mechanism of communication is like kind of wrong. We should actually probably store like we should have like a queue where you can, instead of queuing elements, you just like overwrite the last one. But let's kind of just prove out the concept first, and once we've proven the concept, then we can come back. So we'll say fix me here. Queue will not always provide latest waker. We should have some form of atomic shared value. Not a mutex though, because if it was a mutex, then we'd have a problem where like we can interrupt while the mutex is locked, blah blah blah, and that'd be a problem. So we need some sort of like atomic swap of a reference to some data. Probably what it should be, we could do something like an atomic pointer that we like swap the value out of and free it if we need to, but it's fine, it's fine. for now. Okay. So here he stashes them, and then otherwise he just does. He has to check if he's ready. Sure. But that's only for the time waiter. This guy, he has like a mutex, and this mutex probably doesn't actually propagate to this interrupt context. That will propagate somewhere else to whoever's unlocking mutex. So I think that this actually should go in the implementation for time waiter here. Well, we'll just kind of like chuck this guy in here. So he needs to find like this like waker TX. Great. So here he has waker TX is a reference to a sender. Lock free queue sender of type waker. Great. And where do we construct this guy? Here. Here, so we have our waker TX as part of our service, so we can just say waker TX is mute self.waker TX, which means that this guy needs to have, this is of type a mute, I think like this. All right. Probably we broke some other shit. Yep. We have, our construction is fucked. So this should be called, when we create our queue, we have a waker TX and a waker RX. And these need to get passed into the right places. So this has waker TX here and waker RX here. This is missing field waker RX. Oh, I see. Because when we first construct this guy, he doesn't have any wakers to wake, but on the first poll of the timer, then we will. All right. All right, all right. We've probably made another mistake in here, actually, where on the interrupt side, right now we say, wake up our waker if we have one. Otherwise, skip that wake up. But there's like an order of operations problem in here where I think we have like in maybe like thread 1, we'll call it. Threads aren't really the right nomenclature here, but that's okay. We might say, some shit's gonna happen, and we're gonna say like sleep for a short amount of time. And what that does is that like queues some work to be done on our like service. So we'll have like service thread, we'll call it. And let's say that he doesn't actually like start working. He doesn't get queued till like this point in time, right? Here. So here he'll like propagate the sleep to the interrupt thread. And here's our like interrupt context. Interrupt. So let's say that this sleep should end at like this point in time. Is there like a possible race in here where we don't have our waker before we have the data? And the answer to that is no, because the interrupt handler doesn't actually know that the sleep existed until this point in time. So it's fine. It's fine. I was worried that like we might miss a wake up, but I think we're good. Okay. So can I cargo check now? We're close. This is now a function mutable closure because this wake up, if necessary, takes a mutable self because he might update his waker when he gets one. So that's a problem here. Oopsies. What the fuck did I just do? Terminal got fucked up for some reason. I'll probably hit some set of hotkeys that like breaks tmux that I didn't know about. Okay. So this, because the RTC expects a function closure, and we can just call this function mute. That's fine. I don't think there's any reason this won't work if I just start propagating mutables around. This guy can be also probably take function mute. Cargo check. Is that compile? We're close. 244 and interrupts. This guy, my interrupt handlers probably also have a type of function. So where is this guy coming from? This is handlers is self.handlers, which takes in a box of done function. We can just return these to function mute. Does that compile? No, because somebody has to be browser mutable. So in 134, we just throw a mute on here, I think. Or we say as mute here. This guy has to be mutable. Is this get returns? Aha, this guy on the hash map returns an immutable reference, so I think we can just say get mute here. And now I think everybody's happy. Close, close. In main 224, this guy now has to just be declared mutable. Cargo check. There we go. Everyone's propagated to where they gotta be. We're chilling. So I guess we can try running that and see if it works, because now in our sleep handler, we no longer try to wake up the executor directly. In fact, this future wake up executor function is now no longer used. Great. And so if our sleeps are working correctly, then we can be pretty sure that this is propagating as we expect. So let's cargo run release. And this is running as we expect. However, it's not really fair because somebody else could be waking us up. So I guess let's... what we can do is in our interrupts thing, or sorry, in our future executor implementation, we can just break the normal workflow of calling this wake up execute function, and then we can be pretty sure that if our game loop is running correctly, we are in fact calling that other version. That's great. Otherwise, here we can prove the inverse. So if I go back to my sleep implementation and I comment out this wake by ref somewhere of the propagated waker, I think that we'll just get no movement here. Yeah, see, it's like the game is frozen, but if I uncomment this, we're moving again. So we can be pretty confident that the waker that we've propagated to our interrupt context is in fact making it there and being used reasonably. So we can call this done, and this was done around, this was done at around 43:10 into stream, maybe. Now the next thing we have to do is we need to make sure that we're propagating the latest waker. So we saw these Rust docs that say, on multiple calls to poll, only the waker from the context patch to the most recent call should be scheduled to receive a wake up. So that's a problem for us because we need, with our implementation, we have a queue of depth 1, and if we try to push into that queue before it's been serviced, then we'll drop one, and that's a problem. So we need a new type that's not a lock-free queue. We need some sort of lock-free latest value, lock-free value. And what's going to be in this guy? He's going to have a value. This is going to be a generic type, right? He's going to have some value t, and inside we're going to probably have the value. But this value needs to be able to be atomically swapped out for multiple threads, right? Well, I guess in our case, it's not multiple threads. It's only one thread. Only one thread is calling this service loop. So maybe it doesn't need to be atomic. Let's think about that. Thinking. Yeah, that should be fine. So maybe what happens is inside he has an interrupt guarded value. right? So when we set this value, we turn off interrupts, and when we read it, we have interrupts disabled as well. So we can't ever have like we can't ever have like a collision there that way. That seems reasonable. So we can say maybe we don't even need this like custom type here. Maybe we can just instead of having waker tx waker rx, we can just have like a multiple references to the same interrupts guarded value. So let's think about what that'd be. You would have like a arc interrupt guarded waker. So the idea here would be that you would have one thread might like ship around a reference to this interrupt guarded waker. And the interrupt context would also be looking at them. That's a problem as well. Because if you put these guys in an arc, then like you could accidentally copy this to multiple threads and modify him for multiple threads at the same time, and that would be undefined behavior. So I like the atomic swap version better. That just feels like kind of safer. So we could say struct atomic value or atomic cell. I wonder if that already exists. Rust atomic cell. Somebody's implemented it. It's not in the standard library. Crossbeam atomic cell. The fact that this exists makes me think it's a good idea. And what I would probably do is I would probably just stick an atomic pointer in there and leak it and swap the value inside. But that's not what they do. They have an unsafe cell, so like a mutable value. And how do they do stores? They have this like atomic store, atomic swap. Where do these come from? Are these from within Crossbeam? Atomic store. Oh, this is just a value. So what? They copy the value in, they forget the other one, and then they probably do they use like a fence somewhere? Probably this atomic macro. Probably automatically fences or something. Yeah, this is maybe complex. I think that we could probably implement it with like just a simple. We could do it simpler, right? If we did atomic pointer, and this was of type T. Oops, we have to use core. Is it in core or is it in alloc? I think it's in core. Sync atomic pointer and ordering. And what we could do here is impl T for atomic cell T. So we implement for all generic values, we would implement a function that's like store, and the value is a T. And maybe we take an ordering here even. Like this. And maybe we say, we copy the value out. So we say let vals equal box new val. Right? So we like stick this thing on the heap. We make sure. This is alloc boxed box. We would then like leak the value. Oops, I think you need to say, let me actually import the box type. That's easier. So then we can get rid of these. And I think you say like box leak val. And we could say self. We leak the value. And we say, no, we don't do that. We loop. And we try to store the value. So we do like an atomic store. So we say self.val store. Why is store not auto-completing? Oh, because we don't have this. We don't have a self reference here. Sorry. We would like store the pointer to the value that we just leaked. So we would say what? This is the val as pointer. Can I not get the pointer from a box? Maybe you need like unsave here to do that. As pointer. Is there really no box as like box? There's gotta be a way to get the underlying pointer out of this thing. Is there not? Pin, no, new, leak. Oh, raw? Into raw? Consumes the box, returning a wrapped raw pointer. This pointer will be properly aligned and non-null. The color is responsible for the memory previously managed by the box. How is this different than leak? Oh, because leak gives me the mutable reference, sure. So I want like as raw. Is there like a like I want to like get the pointer out of it without leaking it yet. The idea is that I want to like store the pointer in the atomic and only leak it if it actually made it there. I guess actually I guess what we want to do is we swap the value. Is there like an atomic swap? Atomic pointer. Store swap. Yeah, here we go. Swap takes an ordering route that describes the memory ordering this operation. All ordering modes are possible. Note that using acquire makes the store part of the operation relaxed, and using release makes the load part relaxed. So we probably would just want like a strict ordering swap where we get the old value out. So we can say let previous is equal to, we store the val. We're actually not going to take an ordering here. Fuck that noise. And we're just going to force ordering acrel so that we want to make sure that every store, every time we store, we want to make sure that the previous thing is like dropped correctly. So we're using acrel ordering to make sure that every time we like if like 4 people call this at once, we want to make sure that all 4 get back out in the previous value, basically. Great. This should be swap, not store. And what doesn't it like here? It doesn't like that val is probably, we probably want box into raw on val, like this. Right? And then here, we can say box from raw previous. And this will like create a box and then automatically drop it, which means that like the previous value will be handled correctly. So we'll say let previous equals this, and then we'll say drop previous. Just to make sure that's like clear what's happening. Even though you could just like ignore the value, this makes it like explicit what we're trying to do. We should also probably say if previous is not null. Because the first, we might have nothing in there initially. And we'll say new, gives me an atomic cell of T, and we say we're going to create an atomic cell where the value is a null pointer. I think it's do null mute. Into. Cannot call method on raw pointer with unknown pointy type. Shut up. Okay, this is atomic pointer new, like this. And then we'll do a load. This returns a what does it return? It returns a reference T, I guess. Maybe a mutable reference. I guess we should call this get. Yeah, we'll call this get. And he'll return a reference to T. Yeah, that makes sense. And then we'll say that if you want to mutate, you just fucking can't. Like, screw yourself. And we're just going to put a value in here. Right, when you store, you replace it, just similar to how cell works. And I guess this might return an option to a reference to T, because if we haven't ever stored anything in here, then it's not good yet. And here we will say, we try to get the value out. So we say self.val load this time with ordering acquire, I think, as the read side of this. And we'll say if it's not null, this is val now. If it's not null, what are we going to do? We're going to return some val as a reference. So we're just going to like do like a little type conversion with an ampersand and a star, and otherwise we return none. This seems unsafe, right? Makes sense. So we'll just drop that in unsafe block. And I think that's right. And so now I think what we can do is we can store a shared reference to an atomic cell that we've just created, and use that as our wake up reference. So I think you would have like a arc, atomic cell, waker. Shit. Yeah, that's great. That works for me. And then somewhere else where we inject the waker, instead of having this like queue with a single value of waker that we inject, we're gonna also just call this waker, and we'll also make this an arc atomic cell of waker. And in here we don't have waker tx anymore. We have waker is a reference, doesn't need to be mutable, to waker, and that means here we need this to be a reference to a atomic cell of waker. Cool. This is still called waker tx, so we remove this, and here instead of saying waker tx push, we say self waker store. Great. And this guy doesn't return anything, so we can get rid of that. Cool. And now here we can say if let some waker is self.waker.get. We wake by ref. Cool. So now here instead of making a txrx, we say let waker is a shared reference, atomic shared reference to a atomic cell which we just created. With this initial value empty. And here we say that the waker, the first waker we use is going to be a clone of this because we need to pass them on to the other side later. And then here we just say waker. Cargo check. Sick. And if I cargo run release now, we should hopefully still see our breakout game moving. Great. And we can prove again to ourselves that this is in fact doing the right thing by commenting out the waker use in this one specific case, and we should see our OS lock up, no movement. Let's go. Okay. Very, very cool. So we can call this done at around 58 minutes into stream and 25 seconds maybe. Okay. So now let's try to generalize this a little bit. Generalize atomic cell / waker use. So now that we've done this in one place, we kind of want to like propagate this same pattern to other places. And the question is, how do we do that? So almost certainly we're going to want this atomic cell thing to be in multiple places. Let's actually do a quick checkpoint. We're going to check out a branch that says we're going to call this remove global wake up. Wackapy. Let's call that the right thing. So get, I think it's branch -m for move. Let's actually look this up. -m for move, yeah. Get branch -m. We're going to fix this typo. I'm going to call this remove. Oh my gosh, what am I doing? Remove global wake up. Great. And we're going to just quickly add a little checkpoint. And we'll say checkpoint sleep using new waker. Using waker context. Okay. Status real quick just to make sure. great. This is going to piss me off for forever, so I'm just going to remove this. And okay, so the obvious thing we want to do is we're going to want this atomic cell type is going to be a kind of common type that's used in multiple places. So here we're going to add a pub mod async or atomic cell. And here we're going to move this guy out. So we'll say this guy is gone and he goes to the atomic cell here. And we copy paste every single import so that it compiles. And then we delete the ones that it's bitching about. So none of these, none of these, none of these, and none of these. Unnecessary braces. Sure, you're a little whiny bitch, but I get it. And unnecessary braces. Sure. And then here we want to go back and we want to import this. Okay. These are unused. These are unused. And then we need a create util. Atomic cell. This guy needs to be a public struct. These need to be public functions. Great. Oops. And now probably this compiles. Cargo run, please. Cool. Cool. So let's get status, get add-u, get commit-m, split out atomic cell into own mod. We forgot to actually add the new file, so we get add this guy, get commit amend. Great. Okay. So now I guess what we want to do is we want to start like moving out. We can like look for the go to future and look for uses of this like global wake up execute function. Luckily, there actually aren't that many of them. Let's look at the logger one first. So this just shouldn't be here actually. This log. So this pushes to, oh no, it should. So we have an async queue or an atomic queue, lock-free queue. Sorry, that's the word for it. And here, when we push to him, we need to like tell our executor that we need to service this at some point. And so here, probably what we want to do is we want to do the same thing where our log waiter has an atomic cell of waker. And he is by reference. Yeah, reference here. On poll, he needs to inject the waker. He needs to like propagate the waker to the other side. So here he also needs to be imported. So this is a waker comes from core task. Waker. This guy's an atomic cell waker, so he needs to come from util atomic cell. Great. And here our logger will have to have a waker associated with him. So we'll say waker is a atomic cell waker. Great. Here we need to create him. So we'll make a new atomic cell with who is currently empty. He gets passed in here. Here, instead of doing a global waker, we do self.waker.wake. We do like a little get first. We try to retrieve him. Right, if we retrieve him, then if somebody has ever provided us a waker to use, then we say self.waker.wake by ref. Not self.waker, sorry, waker wake by ref. Great. And then here we need to pass in the waker as a thing to wait for. Cool. And then in our log waiter, we just have to do the same thing where we say self.waker .store cx.waker.clone. Nice. So now every time we push a log, we ask our logger service to wake up with the appropriate waker that he was given by his pull method. Cool, everyone's working. And so now we can actually just go back and we'll go to the last thing we did, which is the interrupts thing. Not interrupts, sorry, in our sleep implementation. And we're actually just going to comment this out again because we want to make sure that now the logger waker is working correctly. So when we cargo run release, what I want to see is our logs getting printed, but the rest freeze. Great. And if I comment back out this wake by ref, what we should see is that our logs don't get printed. And that's true, because what happens is we push logs, and we never ask the logger service to wake up, and so he never gets pulled. Boom. Looks good. Okay. Very nice. So here we do this, here we do this. And here we'll say propagate waker to logger context. And this is done at around 1:06:40. Great. Git commit -m propagate waker to logger. Cool. And I guess what is next here? What is next? I guess we go back to future. We look for this use of wake up executor. And who else is using this guy? Really, not a lot. Not a lot. So here, this is kind of like a hack that we did a couple streams ago, maybe last stream, I don't remember, where we have to busy wait for reasons I don't want to get into. And our way to do that was just to like force our executor to wake up every time. Like we're basically saying like, don't sleep, like always fucking wake up. And I think that here we can just do this. We can do the same thing, but without using the global context. We can just use a local one. Which means that this like wake up executor no longer needs to be imported. I don't think it ever was actually. I think we can test this with cargo test, make sure that our tests still pass. And if our tests exit, then like that was working as expected. Great. Because this is only used in the test context. We're under like a config test here. Cool. And now we can go back and let's see what the last, I think there's only two more. One is in the Ethernet driver and one is in the PS2 driver. I think the PS2 driver is going to be easier to deal with, so I'm going to do that first. PS2 driver being keyboard handling right now. So PS2, I think was personal PS2 name. PS2 server PlayStation 2. Shut up! This is wrong. Google, what are you doing? Feedback. Inaccurate. Incorrect. PS2. You're showing a PS2 connector and saying that it stands for PlayStation. Ah, God. Okay. PS2 port name. Personal System 2 series of personal system computers. Anyways, it's this like non-USB port that's for old ass keyboards. Maybe some still use them. I don't think they do. Anyways, it's like a simpler interface than USB, so I've implemented this first because in the virtual machine I can choose how anything's connected any way I want. Anyways, PS2 keyboard driver, which I think is actually probably misnamed. I think this is a PS2 keyboard and mouse driver, but we called it PS2 keyboard. And what do? We say when we get an interrupt that says that our keyboard has sent us an event, we just unconditionally wake up the executor. And it looks like the only place it's being used is in our like poll read future. Poll read future. Oops, did I just close the wrong window? I did. PS2. Poll read feature. And what does this guy do? he checks the status of the register for the PS2 controller, and he says, if you are ready, then you are ready, otherwise pending. So in here, we need to propagate a waker. So we will do the same thing where we have like waker. Well, I guess I don't know what the type of this is going to be yet. I don't know if this is going to be a reference to a waker or if it's going to be like a reference to a shared reference to waker. I guess in this case, it will always be waker is a atomic cell waker, like we were doing before. And then in here, we're gonna do waker store self.waker.store cx.waker.clone. Easy. Here we don't have atomic cell or waker imported, so we'll say we use util atomic cell, great. Here we're gonna delete this wake up executor call. I guess we'll delete that later. And here we also have to use core task waker. Boom. Boom. Okay. So now here on our read, I guess we're probably going to do a shared reference. So we'll say let waker is an arc new atomic cell new. And the reason I'm saying that we should do a shared reference instead of just like using it raw like we did in the logger is because we're giving a function to this interrupt handler. And this function is going to be like a static function, so we need like a static reference. So like using atomic reference counting allows us to have like multiple references that live for as long as they need to, but will point to the same memory. And here we'll just say if let sum waker is equal to waker get. We do a waker dot wake by ref. Easy. Easy, easy, easy. Here we need to use arc. So this is use alloc arc sync arc, I think. Yeah. And here we need to pass the waker in. So we need to store the waker. So we're gonna say waker here is an arc atomic cell waker. Here we need to clone the waker. So there's this like weird trick that I've seen done sometimes where you like define your lambda inside curly braces. And the reason to do that is you can actually do some like bullshit now where you say let waker is arc clone and waker. And this just means that you can like overload names and still get what you want anyways. And so then here I can pass waker here and it hasn't been stolen. Why doesn't it know the type from this? This should be obvious, right? Because the PS2 keyboard has a defined type, atomic cell waker, and here arc new atomic cell new should give me that correct type. But I guess it doesn't like it, so we'll give it some help by defining the type manually, which is bullshit. And then here we need to say waker is self.waker. Target check. Okay. Now what we can do is we can go and we can look at all these wake by refs and make sure they're all commented out again. Just to make sure that only the waker that we want is the one getting updated. This one doesn't matter, it's only used in testing. So it's just this one left. Cool. And so if I comment this out and I cargo run release, our game should freeze like we expected before. Great. Oh, and I guess even if I like start punching in my keyboard, nothing happens. Great. But now if I in my keyboard drivers have propagated this wake up correctly, I think what should happen is when I press a key, the game state updates. That's kind of fun. It was working for a bit and then it froze. That's kind of interesting. Oh, it's when I start like spamming keys. That's interesting. I wonder what's happening. That's probably worth running the debugger for. That's fucking weird. Oh, if I run debug mode, the frames render so slowly that we never hit the pending state, which is a little bit of a problem. We just get like stuck looping in this like, yeah, that's annoying. Maybe that's fine. Yeah, that's fine. We'll keep this in mind that we saw a hang up when we started spamming keys, and we'll keep an eye out for if that causes any real problems later. It is kind of weird because like other things that should be waking up the executor aren't. And if this is a real problem, it'll like show itself again later when we like refactor the future executor. Okay, so let's look up Waker and just restore these guys to their true beautiful state. And let's look at our diff here. This is fine. And we'll say use atomic cells for PS2 and main. Not atomic cells. We want to use Waker ref. Great. Here we've propagated Waker to... I have been spelling propagate wrong this whole time. It's propagate. Shit. Ugh. My life is so hard sometimes. So we propagated the Waker to PS2 context, and this is 116, 117-ish. And the last one is propagate Waker to Ethernet driver context. There we go. Okay. Where am I? Here we go. So I think this is the last one. Where are we at? Okay, so what happens? Here we are, our interrupt context. Where is it? Where is it? Wow, there's a lot of stuff in here. Interrupt handler is interrupts register. Okay. So here, he just unconditionally wakes up the executor. We can probably do the same thing where we wake up Waker, except here we're in this shitty state where our Waker, our interrupt handler should wake up both the readers and the writers. So we're back in this situation where you could have multiple futures waiting on the same interrupt. And so that needs to get propagated cleanly. Which means something. Which means that we need to keep the state of all of the... We need to keep track of who is waiting on us and wake them all up individually. In fact, we were supposed to do that on the sleep implementation. We just fucking didn't. I just forgot. But that's okay. We'll come back. We'll handle it here first. So, what do we have? We have the service waker is going to be taken in here. And the idea is that we're going to wake up our service future, and our service future will wake up all of the other ones, all the guys who are waiting. So that means service waker comes in here. And this is a arc atomic cell waker. And here we have if let sum waker is equal to service waker dot get. We say waker wake by ref. Get rid of this guy. Here we need to import a few things. So we need to import our atomic cell, great. And this is no longer used, and we also need to use alloc sync arc for our atomic shared reference counted pointer. We also need to use core task waker. And this guy, I like him down here. There's like some sort of form of ordering. For when you see me just like swinging imports around like this, there's like an approximate order that I've like inherited from a previous C++ project that I worked on that I liked, where you basically import the highest level thing first, because like in C++, if you do like include stdi or what is it, IOStream, and then you include my header. If you include them in this order, you ensure that my header, if it needs IOStream, included it himself. But if you include it in this order, you can like accidentally write invalid headers that won't work later. So I have this like in my head, I do this like import ordering of like the most specific thing first to the like least specific thing, kind of like a reverse dependency order. I don't know like what Rust people normally do, but I've just like inherited that, so that's why I've been doing. That's why I do that. Okay. Why is this guy still unhappy? A local variable with a civil name exists. This isn't spelled right. Suriviki. Suriviki Waker. This should be service Waker. Like this. When we initialize this, we need to pass in a service waker. So we'll say let service waker is an arc new atomic cell new. He doesn't have anything in his initial state, but he will later. Probably I'll let cargo format deal with that later if it needs to. If it thinks that line's too long, it probably is. If I set like color call to like 120 set, isn't color column equals 80? Yeah, it's probably going to break that into new lines later, but that's okay. Maybe it does like 100 or 120. I actually don't know Rust's formatting rules. 120, it would like keep it. That's really wide. There's no way it's 120. Maybe it's 100. Who knows? Okay. Sorry, getting distracted. So in here, we need a service function. And what's he going to do? He's going to look at my list of wakers. And he's going to propagate. So he's what he's going to do. He's going to wait on... Sorry, I'm thinking. So he's going to wait for that interrupt to fire. When that interrupt fires, he's going to propagate the wake up to everybody else who cares about it. So here we're going to have like a waker list inside him somewhere. So here we'll say waker list is a what? Like a vector of wakers, except that's not really true. We don't want like a vector because we need to know which future is associated with each one so that when they die that they delete themselves from the list. So you probably want like a hash map maybe. Of like IDs of futures to their wakers. God, that's complex. Right, but if you do it this way, then you could like every time you construct a future, give it an ID, stick it in the list, and when they are done, when the future is dropped, they delete themselves from the list. Great. But is that really how we want to handle this? That's so complex. And also, we only have like our only like interior mutability primitive for this is an async mutex, which you can't use from these from other contexts. I guess we have a spin lock. We could use the spin lock. Then you could use that from the drop context, and in the drop context, you could spin lock, get the map, delete, then delete yourself from it. Is there like a better way? Bum, 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 bum. You could have like a message passing. So from your futures, you could push on drop, you can tell the service through a channel. You could say like, hey, I'm not going to be here anymore. And you could like delete your specific ID. That seems not that bad. There's still like, it's still introducing a weird amount of complexity. But it's probably fine. Yes, let's do that. So how are we going to do that? We can have like a spin lock. I guess we still need a spin lock to work with that. Because to do the message passing on drop, you need to have the context that you want. So let's just use our spin lock on a hash map. And I guess this is a arc spin lock. So here we include util spin lock. I actually haven't, I don't know if this is actually used anywhere, so let's just do a quick sanity check that this is like a sane implementation of a spin lock. We're using sexist ordering. I don't know. SEQCST. We're using that type of ordering, which is probably like a little too strong, but otherwise, this is fine. We could probably, this could be weak. Actually, we'll make the ordering acrel. We don't need such strong guarantees, I don't think. Otherwise, this seems reasonable. So here, we'll use a spin lock on our hash map. That'll make it sync. We should also implement send. We don't need to implement send. It's fine. But we should. So we'll implement send for any spin lock where t is send. Great. And now we will start pulling in types. So here we have collections hash map. It's something that we need to import here. Spin lock is imported. Arc is imported. Unresolved import. Oh, it's because the hash map comes from use. What's the crate name? I'm blanking. Hash brown. Hash map. Okay. So now we have, where did it go? I'm getting so lost. There's too much code. Okay. So here we have a hash map of usize waker, and then we'll say future ID is a usize. And we store all of these things. Our future, I already forgot the name. Future ID is going to be initialized 0. And our waker list is going to be an arc, new, spin lock, new, hash map, new. Like that. Okay. Cargo check. Let's just see if we still compile. We fucked up our spin lock. Atomic loads cannot have release or acrel ordering, right? So the load should be acquire. Right? I think that's right. Acquire when coupled with a load. Yep. Okay, cargo check. Cool, we compile, so everyone's happy. And then here on our service loop, we're going to say, we're going to wait for an interrupt, which means that we have to propagate our waker to the interrupt context. So which means that we need the service waker in here. Just an arc. Atomic cell waker. Atomic cell, not atomic cell, atomic. There we go. Which means that we need to propagate the service waker here. Here we need to clone the service waker. Like this. Great. Bing, bang, boom. Okay. So what happens here? We need to propagate the waker. Waker to interrupt. Then we need to walk list of dependent futures and wake them. Okay, so this part's easy. We say for waker in self, what do we call it? Waker list. But we need to lock the list. Do we need to do like a star ampersand here to get it to deref correctly? Yep. And I think here we say key, we don't care about value, we do. And then we say waker, wake by ref. And here we'll say that interrupt handler only wakes up a single future, but many futures depend on it. These dependent futures will register with the waker list. There we go. In reality, is that, yeah, that's true. That's true. And then here, all we have to do is register the waker. So I think that we can do a little trick here, where you can use futures, future poll immediate, where you pass in a function that takes in, I think, the context. I thought this is how you use it. Poll immediate async. Oh, we pass in an async block. Oops. I thought that you could pass in like a function that gave you the context. Let's quickly pull up the docs. I swear I've seen something where you have like futures, future. Oh, poll function. That's what I want. Poll function, you could pass in something that takes in a context and then it gives you back a poll. Yeah. And here we say cx waker, and we propagate that to self dot service waker store this dot clone, I think. I think that's right. And we say poll ready. Is that true? Do we want to say poll ready here? It doesn't really matter. I think we'll say poll pending. I think that's like slightly more technically correct. And this will just return a poll. Nothing. Okay. That seems reasonable. And now all we have to do is in our polling futures now, we need to like register ourselves with the service function. And we also need to call this externally, but we'll deal with that in a second. So this guy's just async for no fucking reason. Let's fix that. Where is the async part of this? This on read? This read function? Is this not async? Am I high? This should be async. Oh, probably it's because down here. Right. We handle the like waiting for stuff to come in externally. Okay, so this guy needs to increment the future ID register with the future list. Right. Let's think about this. So we have an inner value that we try lock here, or why don't we lock it? Oh, because if it's not available, then we don't want to block forever, I guess. This is weird. I don't know why it's implemented like this. I'm sure there's a reason, I just can't remember what it is. And I didn't write it down. Does it say anything in the blame? This was implemented with help of OSDF Wiki, blah, blah, blah. Initialize the card, provided a buffer, write incoming packets to when an incoming packet is read, up to a circular buffer, blah, blah, on write, blah, blah, blah. Read write has been modeled with 8 functions. These pull a status register for echoing writes and pulls the circular buffer pointers for incoming reads. No, nothing interesting in here. Okay. So what are we going to do here? We are going to update this receiver waiter to take in a future ID and a waker. So here we actually have to get the ID. So we say let IDs equal self.inner. Oh, this is v dot future ID, I think. Yeah. V dot future ID plus equals 1, right? So here we've incremented the future ID internally. We say v dot wake up list. We have to like inject the waker into the wake up list there, which I think means that we have to have a waker at this point. So we can say let waker is equal to future poll function poll ready cx waker dot clone, right? So we get the value out. This is the waker. Here we inject the waker into the wake up list. So we say wake up list doesn't exist. Doesn't exist? What do you mean? What do we call it? Waker list, not wake up list. That's why. So we have the waker list, and what do? We insert at ID the waker. No method named insert for struct this thing. And that's actually not, this is going to be a problem because the waker list needs to be propagated into this receiver waiter as well. So probably what maybe what makes more sense here is we just get the ID. If we fail to acquire the lock, we just continue. But that's a problem because we'll like hot loop forever. Ugh. Ugh. Gross. Gross. So I guess we need to lock the inner thing. I swear though, there's a reason I can't do this. I think that there was like a deadlock somewhere where if we locked, there was like some sort of recursion. Oh no, it was, but that's okay. That's not it because that was what happened was we would lock the mutex, and then maybe we would try to write back from the read callback while the lock was held, and that's not happening here, so that's okay. So we'll say that the ID is equal to, we lock a mutex, we get the ID, we increment the ID. Should be future ID. And then we propagate this back up. And we also have to take the value of the list out of here. So we'll say waker list is also come from this. We'll say let waker list is equal to arc clone inner waker list. Okay, and this guy gets an ID and a waker list like this. This guy needs to be mutable. Great. So now on our receiver waiter, we can take in the ID and the waker list. Great. Now here, he has an ID that's a usize and a waker list, which is a arc spin lock hash map waker hash map of usize to waker list wakers. Something like this. Is that the right amount of angle brackets? Seems like it is. Here we get the waker. And we insert it at the ID. So we say self.waker list lock insert at ID the waker. Perfect. And on drop, we unregister this. So we say impl drop for receiver waiter. And in here, we say self.wakerList.lock remove self ID. Great. Great. So I think that's it. And then we have there's just one last piece here. The right waiter here. He's got to do the same shit. So we have transmit data and wait. So he's gonna say self.future ID, future self.future ID plus equals 1. And he's gonna say here he's gonna pass in the future ID and the waker list. This guy's gonna take those guys in, so he's gonna say future ID is a usize. And the waker list is going to be an arc spin lock hash map usize waker. Right? Which means that now this guy needs the future ID and the waker list. And this transmission waiter implementation is going to look a lot like the receiver waiter implementation. So he's going to have this ID and waker list. Here he's going to have ID as the future ID. Waker list is going to be cloned. And maybe he should just be cloned at the call site instead of here. Right, so it's going to be arc, clone, and waker list like this. Boom. There we go. And then our transmission waiter is going to do the same shit on poll, where he's going to inject himself. And the same thing on drop, where he removes himself. And if I could spell right, transmission waiter. I guess this has just never been spelled right. This should be transmission waiter. There we go. We are very close. Okay. So I think that's it. The only missing piece is this service function is not called. So we need to do that as well. So here in our demo, we'll just chuck in a self dot RTL 8139 dot service. no method named service, because this has to be propagated to the editor type, which is just self.inner.lock.await.service. All right, and let's see if that works. So this doesn't implement start a run. Oh, this actually has to be done in the loop. And he needs to be woken up at a specific time. So he's got the waker in the right spot, so I can just do this. I think. He doesn't ever wait for the interrupt, which is kind of weird. Here I can just say that I'm gonna pull a function that returns. Here we need something to pend. We need something to pend. Which means that we need to implement a quick feature that polls to see if the interrupt service has the interrupt handler is run and asked us to service. Which means that we're gonna have to like stick an atomic bool in here and propagate it. Which I'm going to do off screen because I actually have to take a break like right now. But thanks for watching. If you're watching on Twitch and you want to watch on YouTube, YouTube is linked in the Twitch description. And if you're watching on YouTube and you want to pop by and say hi, I stream most days at around like 1 or 2 Pacific time for like a couple hours. Yeah, thanks for watching. Catch you on the next one. Bye!